We are learning structural geology from last two classes, right? This is the class in which we'll be studying towards some of the new aspects of the structural geology, which are basically joints, unconformity, foliations, lineations, all these things, right? Okay. So I hope my screen is visible to all.
Yes, sir.
Okay. Sure. So starting with the joints. Okay. Starting with joints. Now, joints, and in yesterday's class, okay, I've talked about faults, right? I've talked about the faults. Now, fault itself is a fracture, right? Fault, fault itself is a fracture. Joint themselves are fractures, right? Faults and joints, both these two are the types of fractures. Okay, they are the types of fractures. Say suppose this is the rock mass. Okay, this is one rock mass, and there is a rupture. Okay, there is a rupture or the fracture. Okay, this is the fracture. This line, zigzag line, indicates the fracture, right? Now, both these two, the fault as well as joint, are the fractures. Okay, these are the types of fractures, but there is a fundamental difference between these two. Okay, there is this fundamental difference, is that in case of fault, there is relative movement. Okay, in case of faults, there is a relative movement of blocks. Okay, let us rename these as blocks A and B. Okay, these blocks A and block B, and this block A and B, they will move with respect to each other, right? In case of faults. Okay, in case of faults, these two blocks will move with respect to each other. But in case of joints, these joints, the fractured surface, okay, the fracture surface, say consider this fracture surface. Okay, this fracture surface, there is no relative movement. Okay, there is no relative movement, or the relative movement is negligibly small. Okay, the relative movement is negligibly small. That means the movement, whatever their movement is, that is so small that you can neglect it. Okay, or there is no movement at all, there is just the fracture. Okay, there is just the fracture or the rupture. Okay, just a fracture or the rupture that has been occurred in the rock mass or in the rock body, and it is placed like that itself. Okay, it is kept there like that itself, right? So these kind of structure, okay, these kind of structure will be called as, okay, this kind of structure will be called as the joint. Okay, this type of structure is called as a joint, right? Now, there are these joints essentially are parallel to each other. Okay, these joints, they are essentially parallel to each other like this. Okay, and this forms an array or a large mass. Okay, a large number, a large set of joints, which is called as a joint set. Okay, they are called as the joint set, right? Now, if the joints, okay, if these joints are planar and parallel, okay, if the joints are planar and parallel to each other, that means there is a perfect joint set. So these will be called as systematic joints. Okay, these will be called as systematic joints, right? And all the joint, it is not possible for all the joints to form in a systematic set. Okay, in a systematic set, or in a regular fractures. Okay, in the regular fractures. So these will be called as, or these will be irregular in shape, irregular in fracture, irregular in set. So that will be called as non-systematic joints. Okay, that will be called as a non-systematic joint. Okay, understood this? Systematic and non-systematic. In systematic, you have a parallelism, right? You have parallelism and planar nature of the joints. Okay, the parallel joints are there and they are planar joints, right? So they will be systematic joints. Okay, they will be systematic joints. There is a system, or that joint, entire joint set is following one system, right? It is following one system. but not each and every rock or each and every joint is following the system, right? Each and every joint is not following the system. These joints which are not, okay, these are which are not following the system, or which are not parallel to each other, or which are not even having planar surface, planar geometries. Okay, these planar geometries, those will be called as a non-systematic joints. Okay, so non-systematic joints usually meet but do not cross. They do not cross each other. That means uh, they will be like this. Okay, like this, but they won't cross each other. Okay, they won't cross each other. The smaller joint, okay, the smaller joint will die out at the bigger joint, or that will be called as a master joint. Okay, that will be called as a master joint. Is the largest joint. Okay, master joint is the largest joint, or the large joint, where the non-systematic joints will come. Okay, non-systematic joints will come. Say suppose this is a master joint. Okay, so all the non-systematic joints will will join here. Okay, will join here and die out here itself. Okay, die out here itself. They won't propagate any further, right? They won't propagate any further, or they won't continue any further crossing this master joint. Okay, crossing this master joint, right? Now these joints, how the joints are formed? The joints are formed during the different stages of tectonic evolution in an area. Okay, basically these are the tectonic features. Okay, basically these are the tectonic features, as well as there is some one more interesting feature is there. Okay, which is due to cooling of lava. Okay, which is due to cooling of lava. We'll see in the course of this class, right? So due to the tectonic evolution of the area, okay, during the tectonic evolution of the area, these tectonic evolution will give rise to joints. Okay, so joints, in which rock you will expect the joints? Which rock should be there to expect the joint? Yes,
Igneous.
igneous. Okay, or basically each and every type of rock contains joint. Okay, each and every type of rock can contain a joint, right? There is no watertight compartment that only igneous rocks, or only sedimentary rocks, or only metamorphic rocks will have the joints. Okay, it is not like that. Every rock, okay, every rock will contain joint, or they may contain joint. Every rock may be jointed, right? Say it igneous rock, say it metamorphic rock, say it sedimentary rock. Okay, so more or less each and every rock is jointed. Okay, no rock virtually is a joint free rock, right? Now you can see in these diagrams. Okay, you can see in these diagrams. This one. Okay, diagram A. Okay, this JT1. This one. Can you observe this? There is a gap in between this, right? There is a gap in between the joint. Okay, there is a gap in between the joint, right? Here there is a gap. Okay, when such gaps are developed between the joints, okay, jointed planes basically, not joint, the joint plane. When such gaps are developed, these kind of joints will be called as open joints. Okay, this will this will be called as open joints. Okay, when no such gap is observed, okay, when no such gap is observed, it will be called as closed joint. Okay, it will be called as a closed joint. There is no gap, there is no opening, there is no widening, right? There is no widening, there is no opening. Okay, so it will be closed joint, right? Now joint 3, this one. Okay, this one, this is a smooth joint. Okay, this is a smooth joint. Why it is called smooth joints? Because the joint plane, okay, this joint plane shows a smooth structure. Okay, shows a smooth layer or smooth line, right? It does not have any kind of undulations, it does not have any kind of distortions, hence it will be called as the smooth joint. Whereas in case of joint 4, okay, in case of joint 4, you can see the jointed plane is somewhat undulated. Okay, the joint plane is somewhat undulated. Such kind of joints is called as rough joint. Okay, such joints are called as rough joints. Okay. Then here in a complete rock mass, you can see, okay, in a complete rock mass, joint 5 is there, which is smaller, which is confined to one layer itself. Okay, which is confined to one layer only, or one layer itself, right? These kind of joints will be called as small joints. Okay, because they are confined to only one layer. Okay, because they are confined to only one layer. Okay, and this JT6, that is joint 6, which is continuing in the entire rock. Okay, continuing in the entire rock body. Okay, that will be called as the master joint. Okay, that will be called as master joint. That is the largest joint in the rock mass. Okay, the largest joint in a rock mass, right? So the largest joint in rock mass will be called as the master joint. Okay, now let us try to classify the joints, right? Joints are classified on the basis of their geometry. Okay, the joints are classified on the basis of their geometry and their origin. Okay, their geometry and the origin, these are the two bases of classification. Okay, these are the two bases of classification for any kind of joint. Okay, for any kind of joint. Now on the basis of geometry, okay, on the basis of geometry, that is its attitude. Okay, the attitude of a joint means its dip and strike. Okay, on the basis of its dip and strike, right? So on the basis of dip and strike, the joints are classified into three types. Okay, they are classified into three types, basically four types. Okay, so first one is a strike joint. Okay, first one is the strike joint. Strike joint is the joint sets strike parallel to the strike of the rock. Now understand this. Okay, understand this. Strike joint is the strike of the joint. Okay, the strike of the joint is parallel to the strike of the rock, right? Strike of the joint is parallel to the strike of rock. Okay, so it will be like this. This is the given bed. Okay, this is the given bed or the reference bed for us. Okay, this is the reference bed for us, right? Now here the strike, okay, this strike is parallel. Okay, the strike is parallel to the strike of the rocks. Okay, the strike of a joint, right? The strike of a joint is parallel to the strike of the fault, uh, strike of the bed. Okay, strike of the bed and strike of the joint, right? If such conditions are there, okay, if such conditions are there, the joint will be called as strike joint. Okay, the joint will be called as strike joints. Okay, the strike of the joint should be parallel to the strike of the rock, right? Same way the dip joint. Okay, same way is the dip joint. Now what should be the dip joint? What should be the dip joint then? Joint sets strike parallel to the dip direction of the rock. Okay, so the joint sets strike parallel to the dip direction. Now here dip direction is important. Okay, here you have to find the dip direction. Okay, so joint set will strike parallel to the dip direction, right? It is striking parallel to the dip direction. Okay, it is striking parallel to the dip direction. Now the third one is the oblique fault, oblique joint. Okay, the third one is the oblique joint or the diagonal joint, which lies in either of the angle between dip and strike of the rock. Okay, this can occur in any direction. Okay, this can occur in any direction between dip and strike. Okay, it deep joint and strike joint. So it will have some different angle. Okay, it will have some different angle, its own different angle, so that will be called as oblique or diagonal joint. Okay, it will be called as oblique or diagonal joint, right? Then, so in the stratified rocks, okay, stratified rock means layered rocks. Okay, in the layered rocks, the joints may develop essentially parallel to the bedding planes. Okay, where the bedding planes will be however how the bedding planes are there. Okay, how the bedding planes are there, like that bedding planes, the joints will be, okay, these joints will be present, right? So these kind of joints, okay, these kind of joints are called as bedding joints. Okay, these kind of joints will be called as the bedding joints. Okay,
सर एक वेळ डीप जॉइंट डायग्राम वर एक्सप्लेन करा सर.
deep joints, see, this is a deep joint D. Okay, this one, डीप जॉइंट म्हणजे काय, डेफिनेशन काय त्याची?
Strike of joint parallel to deep direction of rock.
Deep direction,
हाँ.
deep direction, right? So deep direction should be parallel. Okay, deep direction should be parallel to the strike of the rock bed. Okay, deep direction should be parallel to the strike of the rock bed. ठीक आहे, असं म्हटलंय त्याला. ठीक, काय म्हटलंय, जॉइंट सेट स्ट्राइक पॅरलल. ओके, नाही, जॉइंट सेट्स स्ट्राइक पॅरलल टू द डीप डिरेक्शन ऑफ द रॉक. ओके, joint set the joint set strike parallel. Okay, joint set strike parallel to the dip direction of the rock. म्हणजे रॉकची डीप डिरेक्शन, ठीक आहे, रॉकची डीप डिरेक्शन आणि जॉइंटचा सेट, ठीक आहे, जॉइंट, दोज शुड बी पॅरलल. ओके, दोज शुड बी पॅरलल. This is the dip direction of the rock, correct? This is the dip direction of the rock, and this is the strike of joint. Okay, this is the strike of joint. So these are parallel, right? These are parallel. Okay,
Yes, sir. Got it.
this should be parallel, right? This should be parallel, and in this case, this will be called as a deep joint, right? Now, in a stratified rock, right? In a stratified rock, when the stratifications are there, right? When the stratifications are there, in the stratifications, the beddings, okay, the beddings or the jointing will form along the beds itself. Okay, the joints will form along the bed itself or according to the beds themselves. Okay, it will be called as the bedding joint. Okay, it will be called as the bedding joint, right? So these are the basic four types of joints. Okay, these are basic four types of joints or on the basis of their geometries. Okay, the four types of joint based on their geometries. Okay, so bedding joint, strike joint, deep joint, and oblique joint or diagonal joint, right? These are the four basic types of joints on the basis of their geometries. Next, on the basis of the classification on the basis of genesis, how do the joints originate? Okay, how do the joint originate? Right now, as I've told you in the starting of the class, that the joints are formed. Okay, joints are formed due to tectonic forces, right? Majority of the joints are formed due to the tectonic forces. Now here the tectonic forces will act. Okay, the tectonic forces will act and they will give rise to this joint. Okay, the first one is the tension joints. Okay, the first one is the tension joints, which are developed due to the tensile forces acting on the rocks. Okay, the tensile forces which are acting on the rocks. So the most common locations, okay, most common locations for the tension joints are the outer margins of crests and troughs in the folded sequences. If the sequence is folded, if the rock is folded like this, okay, if the rock is folded like this, right, where should be tensional joints? At these areas. Okay, these are the areas where there is maximum tension, right, where there is maximum tension, because it is the hinge. Okay, it is the hinge, the point of maximum curvature, right, it is the point of maximum curvature. So at the maximum curvature there will be highest tension, right, at the maximum curvature there will be highest tension, and the probability of breaking the breaking any material, okay, the probability of breaking any material will be highest there, right. If this entire fold has to be broken, okay, if this entire fold has to be broken, which will be the easiest spot to strike, okay, which will be the easiest spot to strike, this one, hinge, right, the hinge, just strike on the hinge, okay, strike on the hinge, and you will get, you can easily break the fold, okay, you can easily break that rock, right. So these tensional joints, okay, the tensional joints will be developed in the outer margins of this crest here, in these locations, okay, in these locations, right, crest and the troughs of the folded sequences. These are generally formed due to these tensile forces, okay, formed due to the tensile forces, okay, which will be coming, or which will act on this kind of folded structures, okay. Next is the shear joints. Okay, next are the shear joints. Now in the shear joints, these are observed in the vicinity of the fault planes, which are near the fault planes. Okay, fault planes and the shear zones, where the relationship is with the shearing forces is clearly established due to shearing basically. Okay, these shear joints are formed due to the shearing forces. Okay, due to the shearing forces. They are due to this kind of shearing forces due to the friction, okay, due to this frictional action. So in the fault planes, okay, in the fault planes, if say suppose this is the fault, okay, if say suppose this is a fault, you can easily find cracks or fractures or joints near these fault planes, okay, near the fault plane, okay. So this will be called as shear joints, right, and compression joints, which are exactly opposite to that of the tensional joints. Okay, tensional joints again formed in the folding process, okay, again formed in the folding process, generally formed in the folding process, but in this case they are found into the core body, okay, the core of the fold. Here there will be compression, right, here there will be compression, and due to compression, okay, due to compression or crushing, there will be crushing or compression here, okay, and not here, okay, in these internal parts, okay, in these internal parts there will be compression, in the outer external part there will be tension, right. So here there is the compression, and this compression will give rise to these compressional joints, okay, this will give rise to these compressional joints, okay. So you can observe this here in this diagram. These are tensional joints, okay, these are the tensional joints which are found here. These are the compressional joints, okay, in the core part, okay, in the core part of the fold, okay, core part of the fold, and these are the shear joints, okay, here there is faulting. Okay, here there is faulting, and this faulting is giving rise to this kind of jointed structures. Okay, it is giving rise to this kind of jointed structures, which will be called as shear joints. Okay, this will be called as the shear joints, right? Understood this? Compressional joints, tensional joints, and shear joints. These are the three types of joints. Okay, these are the three types of joints which are formed due to the tectonic forces. Okay, due to this tectonic forces. Right. Now there is one more type of joint which is very beautiful to see. Okay, it is very beautiful to see, and it is very beautiful structure. Right. This is called as columnar joint. Okay, that will be called as the columnar joint. These columnar joints, okay, these columnar joints are typical of the volcanic igneous rocks. Okay, volcanic igneous rocks. And generally, they are found in basalts. Okay, in the basaltic rocks, right? So they are typically of volcanic igneous rocks. Now, it is produced by cooling of lava flows. Okay, it is produced by cooling of lava flows, then ash flow tuff, and other bodies of magma or lava. Basically, this is the cooling of lava structure. Okay, this is the structure which is formed due to the cooling of lava, and large scale lava cooling will be there. Okay, and it will form this kind of structure. Okay, now cooling causes contraction. Okay, wherever anything is getting cooled, okay, whenever anything is getting cooled, it will have a contraction. The volume will be reduced, right? The volume will be reduced. Only exception to this rule is water. Okay, only exception to this rule is water, because water expands its volume on cooling. Okay, that too in the when it forms the ice. Okay, when it forms ice, then its volume increases. But every other material or every other body in the earth, in the nature, reduces its volume. Okay, reduces its volume when it is getting cooled. Okay, so when anything is getting cooled, say you can do this experiment. Okay, make the glass red hot. Take any glass. Okay, take any piece of glass, make it red hot and put it into ice water. Okay, put it into ice water, it will immediately chill, it will immediately cool, its temperature will drastically will reduced, and it will shatter into pieces, right? It will shatter into pieces, it will completely be broken, it will completely be cracked, right? Why is it so? Because this kind of cooling, okay, this kind of sudden cooling has led to formation of the fractures. Okay, has led to the formation of the fractures, and these fractures, okay, these fractures in case of lava, okay, in case of lava, they form the joints. Okay, they will form the joints. Okay, so these fractures, the fractures will be formed, and these fractures will propagate from top to bottom. Okay, they will propagate from top to bottom of the flows inwards towards the center. Okay, you can see this in this diagram. Okay, here there is contraction. Okay, here there is the contraction. Entire magma or entire body is getting uh, is converging towards the center. Okay, it is flowing towards the center. Okay, and this will develop the cracks. Okay, this will develop the cracks. Now the predominantly hexagonal pattern arises because contractional stresses is most efficiently relieved by three fractures that intersect at angle of 120 degrees. Okay, which in turn creates six sided polygons. Okay, so there is a contractional stress. Okay, this contractional stress, so this contractional stress creates a beautiful structure or these angles. Okay, these fractured angles at 120 degrees. Okay, it creates that angle of 120 degrees, and it creates this angle will create these six sided polygons. Okay, this will create six sided polygons, and this will give its the columnar basalt. Okay, this will give the columnar basalt its characteristic shape. Okay, the characteristic shape of hexagon. Okay, the hexagon or hexagonal pattern. Okay, now these columns are oriented perpendicular to the main cooling surface or lava flows and other igneous bodies, right? They are oriented perpendicular to the main cooling surface of lava flows, so it will be standing erect generally. Okay, it will generally stand erect like this. Okay, so it will be perpendicular. It will orient its perpendicular itself as perpendicular to the main cooling surface of the lava flows and other igneous bodies. So whatever the lava flows is, okay, whatever the lava flow is and whatever the cooling igneous bodies are, okay, whatever the cooling igneous bodies are, it will orient itself perpendicular to the main cooling surface, right? Got this? So this is all about, okay, this is all about joints. Okay, this is what you need to know about the joints, right? Understood? Anything you have, any question in mind, anything you want to ask, or shall we continue further?
Continue.
Okay, so this is all about the joints. Now I'll move towards another structure. Okay, I'll move towards another structure which is not actually the structure but it is a phenomenon. Okay, is it visible now?
Yes, sir.
Yes, sir.
Okay, so we'll start with the new topic, and that will be unconformity. Okay, that is the unconformity. Now, what is unconformity? Unconformity basically is the break in the stratigraphic sequence. Okay, this is the break in the stratigraphic sequence. Now there is one bed which has been interrupted, or it has stopped deposition. Okay, that bed has stopped deposition, and another bed or the deposition is yet to come. So that difference, okay, that difference, that time gap, okay, that time gap, which will be shown, or which will be seen as erosion. Okay, either erosion or non deposition. There won't be any kind of deposition either, or there will be erosion, right? There will be erosion. So which will, it will show, okay, it will show a break in the stratigraphic record. Okay, it will show the break in the stratigraphic record. There won't be a continuous record, right? There won't be any continuous record that 1 2 3 4 and 5. No, not like this. There will be 1 2 3. After that 4 will be 4 will not be there, and then some different stratigraphic sequence may start, right? Some different stratigraphic sequence may start. So these kind of structures, or these kind of break in the stratigraphic sequences, okay, this kind of break in the stratigraphic sequences will be called as unconformity, right? It is generally referred to as the period of non-deposition. Okay, it is generally referred to as the period of non-deposition. You can conveniently call it as the surface of non-deposition. Okay, you can conveniently call it as the surface of non-deposition or surface of erosion during the stratigraphic sequence, right? Now, the recognition of structure, this unconformity, okay, recognition of the unconformity is of considerable importance in the structural geology, because identify, you have to identify why is it these unconformities are so important. Okay, why these unconformities are so important? Because it gives the age relationship. Okay, it helps establish age relationship. Which of the which bed is older, which bed is younger, what are the tilts, what is the original structure. Okay, what is the original structure, which kind of which kind of origin of the rock might have been there, right? as well as as well as they are economically important. Okay, unconformities are economically important. You might have heard about unconformities in Vindian group. Okay, in the Vindian supergroup, all the unconformities in the Vindian supergroup are diamondiferous, right? They are diamondiferous. We can recover diamonds from them, right? Also, these unconformities, okay, these unconformities have given the fossils as well. Okay, they have given the fossils, so that these these kind of unconformities are very much useful to know or to decipher the life of that area. Okay, the life forms of that area, right? Hence these unconformities are so much important, right? So it serves as an important marker surface during geological mapping, right? During geological mapping, it is very much easier for to demarcate or to delineate the difference between the two beds, bed A, bed B. In between there, if in between there is the unconformity, right? It records vertical movements leading to emergence. Okay, may give us the age of folding or vertical movements. What is the age of folding? Whether it is younger, whether it is older. Okay, and in many cases enable us to distinguish between the different tectonic units. Now this is important, right? Which kind of tectonic event might have occurred earlier, which kind of tectonic event might have occurred later in a same area, right? In a same area which is bounded by unconformities. Okay, which is bounded by unconformities. If there are several unconformities, okay, if there is an unconformity in the area, okay, in the area, so you can identify or you can establish these kind of relationships. Okay, you can establish these kind of relationships, different tectonic units, because there are several tectonic units which lie below the unconformity, so they will be formed uh, earlier to the unconformity, that is they are older, and newer will be some newer tectonic units may show some different kind of orientations, may show some different kind of characteristics, right? So it will help us to establish or to distinguish between these kind of tectonic units, right? So this age of an unconformity lies somewhere between that of the youngest rock of the lower unit and that of the oldest rock of the upper. Okay, that means, okay, the white indicates unconformity. Okay, the white indicates unconformity, and the age relationship. Okay, if you have to calculate the age of the unconformity. Okay, age of the unconformity. So this age of the unconformity will lie somewhere between these two. Okay, somewhere between these two. Okay, so the youngest rock of the older unit, this is the youngest rock, right? This is the youngest of older, and this is the oldest of the upper, right? This is the oldest of the upper, and this is youngest of the lower. So the age of the unconformity will lie somewhere in between these two. Okay, somewhere in between these two, right? Now in most cases a mappable unconformity. Okay, the mappable unconformity represents an erosional surface. So larger unconformities, basically they are the erosional surfaces. Okay, they are the erosional surfaces. They erode the originally present material. Okay, they erode the originally present material, and they now establish something different rock above them. Okay, so the common sequence of geological event is the folding of sequences of sedimentary rocks. Say suppose there is nothing, the planar area. Okay, there was a planar area like this. Okay, then due to the tectonic movement or tectonic disturbances, this area got folded. Okay, this area got folded and took the shape like this. Okay, took the shape like this area got folded and it folded like this. Okay, now tectonic forces stopped working or slowed down working. Okay, slowed down working, it won't stop obviously. Okay, it has slowed down. So the other agencies, which are the natural agencies, okay, natural agencies like wind, like water, they got the chance. Okay, these got the chance to erode this upper surface. Okay, to erode the upper surface, basically it will try to erode everything, but the area of influence, okay, the area of influence of the natural agencies will be that in which the upper one or the higher ones, right? So these are the higher elevated areas. Okay, these are higher elevated areas, so that they will act on these areas. Okay, they will act on these areas, and eventually they will erode these areas. Okay, eventually they will erode this area. Okay, now what we have left with? We have left with the lowermost portion. Okay, we have left with this lowermost portion and one surface. Okay, and one surface which is an erosional surface. Okay, which is an erosional surface or erosion surface. Erosion surface is that surface where erosion has occurred. Okay, where erosion has occurred, so this surface will be erosion surface, right? This surface is the erosion surface. Now the work of natural agencies is going on. Okay, the work of natural agencies is going on. It has not stopped. So due to flowing wind or due to flowing water, some more deposits or some more material have come. Okay, materials have come, and these material have been deposited in a layer manner. Okay, it has been deposited in a layered manner, right? So first there will be larger materials like boulder, like cobbles. Okay, cobble, pebble materials. These will be deposited, and the smaller materials will be deposited in the upper part. Okay, in the upper part of the succession. That means it will create a stratification or layering. Okay, it will create a stratification or a layering. Now observe the basement and the this older form, this older rocks, and these are the newer rocks. Okay, observe the relationship between these two. Okay, observe the relationship between these two. You will come to know that there is an angular relationship, right? There is an angular relationship. Such kind of angular relationship is called as angular unconformity. Okay, such kind of angular relationship will be called as angular unconformity. So the angular unconformity is that in which there is an angular relationship between basement and its cover. Okay, basement and its cover, that means the overlying rocks and the underlying rocks, right? So underlying rocks will be at some angle. Okay, the underlying rocks will be at some angle, and the overlying rocks generally are horizontal. Okay, they are generally horizontal, right? So it forms a striking angle here. Okay, it forms an angle, and this angle, this kind of angular relationship is termed as this angular unconformity. Okay, this kind of relationship is called as angular unconformity, correct? Now this angular unconformity, okay, the angular unconformity helps us to distinguish between the older and younger tectonic events. Obviously, right? Obviously, folding has occurred younger to the older. Okay, folding has occurred older to the sediments, right? First there was folding. Okay, first there was folding like this, and then the sedimentation has occurred. Okay, then the sedimentation has occurred. There is it possible that first sedimentation has occurred, then folding occurred, then the sequence got interchanged? It is impossible, right? It is impossible in nature. It is completely impossible in nature that first the sedimentary cover has formed, then the folds have formed, then the fold was got broken. The folds got broken into the upper surface has got broken, the lower surface has remained. So lower surface automatically came downwards, and upper surface, these upper surface leaving the flat one. So these horizontal beds came and placed themselves over the fold. Is it possible? Not at all, right? Not at all. So it is not going to happen. So this angular unconformity angular unconformity helps us to distinguish between these older and younger tectonic events. So which tectonic event has occurred first? Okay, which tectonic event has occurred first will be or can be identified through this angular unconformity. Okay, so because of the angular unconformity, the geometry of fold produced by the second deformation will be different in the rocks lying above and below the unconformity, right? If there is further folding, Okay, if there is further folding, it is not necessary that horizontal beds are only the way. Okay, the horizontal beds are deposited. This is not the only thing which is possible. Okay, there can be, right, there can be further folding as well, right, there can be further folding, but the orientation of the folding, okay, the orientation of the fold below unconformity and above unconformity will be different. Okay, below unconformity and above unconformity will be different, their orientation will be different, its geometry will be different, right, the orientation will be different and in its geometry will also be different, right. So this is angular unconformity, and angular unconformity is the most important unconformity, right. Now there are again two types of unconformities. Okay, non-conformity. Okay, non-conformity. Non-conformity is the erosional unconformity above a massive plutonic rock. Okay, above a massive plutonic rock. That means there is a plutonic rock here. Okay, there is a plutonic rock here, and above it, okay, above it, the deposition has occurred. Okay, there the deposition is occurred. So this kind of unconformity will be called as a non-conformity. Okay, this will be called as non-conformity, right. I'll show you in this diagram, this diagram see this. Okay, this is your angular unconformity. Okay, this is your angular unconformity. See here, there is angular relationship between the basement, okay, between the basement and its cover. Okay, basement and its cover. Okay, B, it shows non-conformity. Okay, it shows non-conformity. This is plutonic rock, okay, or igneous rock, plutonic igneous rock, and above plutonic igneous rock we have the sedimentary cover. Okay, the sedimentary cover, and this kind of unconformity will be called as non-conformity. Okay, this kind of unconformity will be called as non-conformity, right. A disconformity. Okay, next type is the disconformity. It's a type of unconformity in which the beds above and below, okay, beds above the unconformity and below the unconformity, right, beds above the unconformity and below the unconformity, both will be parallel. Okay, both will be parallel to each other, right, both the beds will be parallel to each other, right, these beds and these beds are parallel to each other. This shows unconformity. Okay, this shows the unconformity. So below the unconformity and above the unconformity, both the beds will be parallel to each other, right. So in many cases, two units above and below the disconformity are separated by an undulatory erosional surface. There is an undulatory erosional surface. Okay, there will be the undulatory erosional surface. So this erosional surface of unconformity shows a conspicuous border. The relief basically means the border. Okay, so the unconformity may be difficult to recognize in such cases. So thus the limestone strata lie disconformably on other strata of limestone without clastic zone between the two sets. Such obscure relationships have been described as paraconformity. Okay, there is para conformity. That means limestone strata is there. Okay, limestone strata is there, there is no clastic strata. Okay, one limestone strata lies above another limestone strata. Okay, यहाँ भी limestone, यहाँ भी limestone. Okay, यहाँ भी limestone, इधर भी limestone. ठीक है. So these kind of zones might be observed. Okay, these kind of zones might be observed in which, okay, in which there is no clastic zone in between. in between these two zones or two sets. Okay, in between these two sets or two zones. So it is difficult to recognize. Okay, it is difficult to recognize. Okay, you can see here the diagram D. Okay, this diagram D, it shows paraconformity. Okay, it shows the paraconformity. This is one limestone bed, this is another limestone bed. Okay, this is one limestone bed, this is another limestone bed, and there is no sign of any kind of uh, clastic sedimentary rocks or clastic rocks present here. Okay, there is no sign of any clastic rock present here, and hence this will be called as the paraconformity. Okay, this will be called as paraconformity. Okay, now how will you identify the recognition of the unconformities? Okay, the recognition of the unconformities. Now there are three broad classes of criteria. Either it should be structural, sedimentary, and paleontological. Okay, these are the three criterias. Okay, these are three criterias with which you can identify or you can recognize the unconformity on the field. Okay, either go for structural or sedimentary or paleontological. Okay, so most commonly used, okay, most commonly used are the structural, and these are the angular unconformity. Okay, this is the most commonly used and uh, most commonly seen. Okay, most commonly seen. Okay, so angular unconformity, and the disconformity represented by an undulatory surface which is produced by erosion. Okay, which is produced by erosion and emergence, and which cuts across the bedding planes of the underlying formation. Okay, so मोस्ट कॉमनली कौन से कौन सा मिलेगा आपको? सबसे कॉमनली मिलने वाला, या फिर मोस्ट कॉमनली ऑब्जर्व, मोस्ट कॉमनली एनकाउंटर्ड, right? The most commonly encountered are the angular unconformity and disconformity. Okay, and I told you about the angular unconformity. You have to go for the angular nature of the rocks. Okay, you have to see the angular nature of the rocks. And in case of disconformity, okay, in case of disconformity, what you have to see is this undulatory surface. Okay, this undulatory surface. Okay, and this undulatory surface will show or will give the evidence of presence of disconformity, right? So the unconformity can be easily recognized when flat lying. If it is flat lying, then it can be identified. Undeformed or weakly deformed sediments of younger age overlay an older group of schists and gneiss. So it is very much very much easier for us to identify if the basement, okay, the basement of the unconformity, okay, the base of the unconformity is of schists and gneisses, that is of metamorphic rock, and above that, okay, above them the rocks which are of the younger age, and that too they are the sedimentary rocks. Okay, they are the sedimentary rocks, and if they are flat lying or undeformed or weakly deformed rocks, okay, if weakly deformed rocks or undeformed rocks, it will be easier for us to identify. Okay. The older crystalline rocks in such situations are generally described as basement. Okay, which I am referring to basement right from the starting of the class. Okay, so this is the basement. So it is described as a basement. So older crystalline rocks which are present at the base. Okay, the older crystalline rocks which are present at the base, this will be called as, or this will be described as the basement, while the overlying sedimentary strata, okay, overlying sedimentary strata is called as cover. Okay, so it will be basement. So if say suppose, okay, if say suppose this is the older rock, the crystalline rocks which are present, and these are the newer sedimentary rocks. So this will be called as basement, and this will be called as cover. Okay, this will be called as basement and cover, and the relationship between these two, okay, the relationship between these two will be described as the basement cover relationship. Okay, the relationship between these two will be described as the basement cover relationship of the unconformity. Okay, basement cover relationship in the unconformity, right? Got this?
Yes, sir.
So these are the two important structures which we have to see. Okay, that is joints and unconformity. Okay. Next, foliation. Okay, the foliation. Now, what is this foliation? Foliation is generally used for any fabric forming planar or curvy planar structure in a metamorphic rock. Now, understand this thing. The structures or structural geology is best studied in metamorphic rocks. Okay, it is best studied in metamorphic rocks. So, majority of the things will be observed in metamorphic rock themselves. Okay, majority of the structures, majority of the features which we have seen so far. Okay, those will be best observed in the metamorphic rocks. Okay, those will be best observed in metamorphic rocks, right? But may also include primary sedimentary bedding or magmatic layering. Basically, what foliation actually is, okay, what foliation actually is the layered arrangement like this. Okay, layered arrangement like this. You might have seen the shell. Okay, you might have seen the shell, or you might have seen the slate or fillet. Okay, shell, slate, or fillet. You might have you might have seen this in this course of years, right? That is nothing but the foliation. Okay, that is nothing but the foliation, right? Now there are two types of foliations. Okay, two types of foliations: primary foliation. Okay, primary foliation, secondary foliation. Okay, so the primary foliation that forms during the deposition of the sediments, right? That formed during the deposition of the sediments and formation of the magmatic rocks when the rock is getting deposited. Okay, when the rock is getting deposited or when the rock is forming. Okay, when the rock is forming, it will generate the foliation, and that will be called as primary foliation. Okay, it will generate the foliation and that will be called as primary foliation. And the secondary foliations, okay, secondary foliations are such that axial plane cleavages in the metamorphic rocks. So original cleavages or original foliations that have been retained, right, that has been retained during the metamorphic processes. Okay, during the metamorphic processes, or the metamorphic processes has have given the given rise to the foliation or the foliated structures to the in the rocks. Okay, in the rocks, that will be called as the secondary foliation. Okay, that will be called as the secondary foliation. So the primary foliations are beddings in sedimentary rocks. Okay, beddings in sedimentary rocks, flow banding in lavas, and magmatic layering in intrusive rocks. This can be a question for you. Okay, this can be a question for you. Bedding in sedimentary rock is an example of, okay, bedding in sedimentary rock is an example of, flow banding in lavas is an example of, right? Or which of the following is an example of primary foliation, right? Which of the following is the example of primary foliation? This kind of questions might be asked, right? And same story, okay, same story holds true for the secondary processes as well, or the secondary foliations as well. Okay, the secondary foliations are the products of stress and strain. Okay, these are the products of stress and strain, and most are tectonic foliations because they form in response to the tectonic stresses. Okay, they form due to the uh, in response to the tectonic stresses, right? So these are the secondary foliations, right? Now, a tectonic foliation, okay, a tectonic foliation is a planar structure which is formed by tectonic process and includes cleavage, schistosity, and myelonitic foliations. So, cleavages, schistosity, and myelonitic foliations are the parts or the types of the foliations. Okay, cleavage and schistosity, khas. Okay, cleavage and schistosity. Remember this. Okay, specifically remember these two, cleavages and schistosity. They are the parts of the foliations. Okay, they are the parts of the foliations, right? So foliation is a fabric, which means that a single surface such as fault or joint will not represent a foliation. So single surface will not represent a foliation, right? Single surface will not show the foliation. What you have, you need to have a stack of surfaces. Okay, you need to have a stack of surfaces like this. Okay, or with a very simple example, a very simple example of a book. Okay, so I have this book. Okay, I have this book and I have this surface. Okay, I have this one surface, right? So will it be called as foliation? Will it be called as foliation? Is it foliation or is it a plane?
Plain.
It is simply a plane, right? It is simply one plane. It is not a foliation, right? Because it does not have anything to correlate with. Okay, it does not have anything to correlate with. Now I am putting some pages over it. Okay, I have put some pages over it, right? Now all these pages, okay, all these pages are parallel to each other, right? All these pages are parallel to each other, and each of these pages have the same orientation. Okay, each of these pages have the same orientation in the same direction, right? So these kind of structures, okay, these kind of structure will form, okay, will represent a foliation. Okay, this kind of structure will represent a foliation, right? So fault or joint, there are basically the planes. Okay, faults and joints basically are the planes, and they will not show foliation. Okay, they will not represent the foliation. The foliation will be represented by stack of the surfaces. Okay, stack of the surfaces. Okay, now even if the parallel fractures are distributed throughout a hand sample, they may lack the cohesion. That is a second characteristic of foliations. Now second characteristic of foliation is that, okay, second characteristic of the foliation is that there should be cohesion, right? There should be cohesion. Now what is this cohesion? Cohesion is the degree or property of the rock of compactness. Okay, it is the property of compactness. That means the rock should be compact enough. Okay, the rock should be compact enough. The layers should be compact enough to hold the foliations in place. Right, to hold the foliations in place. Now I'll take the same example once again. Okay, I'll take the same example once again. Right, again this book. Okay, is there cohesion? Is there cohesion?
No, sir.
Is it compact? Is it compact?
No.
I suppose it is not. Okay, this is not that. This is not compact. Okay, if it was compact or if it were compact, then these kind of folding or these kind of turning pages would not be possible, right? This kind of turning pages would not be possible, right? So these rocks, okay, these rocks, they should have or they must have cohesion. Okay, they must have cohesion. That means they must be strong enough. Okay, there must be strong enough to hold the foliation in place, right? To hold the foliation in place. Although, if you try to break the rocks, okay, if you try to break such rocks, they will easily be broken through their foliated surfaces. Okay, through their foliated surfaces. But these splits or these foliations, okay, they need certain amount of force. Okay, they need certain amount of force, and that force is required to overcome the cohesion. Okay, the force which is required to overcome the cohesion. Okay, so the force applied, okay, force applied on the rock, on this rock or on these foliated surfaces. Okay, the force applied on these foliated surfaces should be more, okay, should be more than that of the cohesive force. Okay, than that of the cohesive force, and that will give you the split or the pieces of the rock. Okay, pieces of the rock along its foliation, along its planes of foliations. Okay, along its planes of foliations, right? Understood? So a foliated rock is by definition cohesive. Okay, it's by definition cohesive. It should be or it must be cohesive. Although rocks may split preferentially along the foliations, right? So rock will choose to break along the foliation itself, right? The rock will choose to foliate, or the rock will choose to break along the foliation itself. Okay, along the foliation itself, but it should be or it must be cohesive. Okay, it must be cohesive, right? Understood this? So this is all about cohesion. Okay, this is all about the cohesion or the foliations. Okay, this is all about the foliations, right? Now the next aspect is the lineation. Okay, next is the lineation. Now what is this lineation? As the name itself indicates, lineation. Lineation means any linear structure or linear element. Okay, any linear element which occurs in a rock. The linear elements which occur in the rock, such as linear structures. Okay, such as these linear structures. Mind you, this is not lineament. Okay, this is not lineament. Lineament is different, right? Lineament is different, lineation is different. Okay, so lineation is the term which is used to describe linear elements that occurs in a rock. Okay, that occurs in a rock. So the definition, going by the definition, the lineation is a fabric element in which one dimension is considerably longer than the other two. Okay, one dimension because it is a three-dimensional structure. Okay, this is a three-dimensional structure. In this, one dimension is considerably longer than other two. For example, this pen. Okay, for example, this pen, right? This is a linear body, right? This is a linear body. Why is it a linear body, or why I can call it as a linear body? Because it's one direction or one dimension. Okay, this one dimension is considerably longer than its other two directions. Okay, other two dimensions, right? So large number of non-tectonic or primary linear structures occur in both undeformed and deformed rocks. May there be deformed rock, or may there be undeformed rocks. There might be linear structures present. Okay, there might be linear structures present. Okay, ropy lava, flow lineation, columns in columnar basalts. We have just seen what are these columnar basalts, columnar structures or columnar joints. Okay, and long axis of aligned non-spherical pebbles, grooves, they mark and align fossils in sedimentary rocks are some examples. These are the examples of lineations. Okay, these are the examples of lineation. Okay, uh, make this or mind these examples. Okay, learn these examples. The columnar basalt, a longer structure. No, I'll take these pictures in your mind. Okay, columnar basalts, then long axis of aligned non-spherical pebbles. Okay, stretched pebbles are there. Then groove marks, then aligned fossils in sedimentary rocks. Sedimentary rock in the fossil, they might some this alignment might be there. Okay, alignment might be there. Okay, so these are some of the examples of the lineation. Okay, these are the examples of the lineation. Now see this. These are the lineation. This is how lineation looks like. Okay. In a rock, these are the lineations. Okay, this is basically, this structure is called as budinage. Okay, this structure is called as budinage structure. This individual layer or this individual part will be called as a budin. Okay, this like this. This will be, okay, this individual structure or individual part of this large structure will be called as a budin. Okay, here there is the lineation which are formed due to folding. Okay, lineations which are formed due to this folding. Okay, you can see here this long lineations are there. Okay, these longer structures, linear structures are there. These will be lineations. Okay, there will be these lineations, right? Now the fabric elements consisting tectonic linear structures, okay, include elongated physical objects. Okay, elongated physical objects just like strained mineral aggregates or conglomerate pebbles, the stretched pebbles. Okay, stretched pebbles like this. Okay, the pebbles get stretched. Okay, then lines of interactions between two sets of planar structure, just we have seen in the previous diagram. Okay, we have seen in the previous diagram. And geometrically defined linear features such as fold hinge lines and crenulation axis. Okay, so these are the tectonic linear structures which are found due to this, or these are the fabric elements, okay, which constitute or which forms the lineation in any area or in any structure. Okay, so distinction is made between penetrative lineations which build up a linear fabric or L fabric. Linear fabric is there. Okay, the lineation is there, so it will be called as lineation, linear fabric. So, or for short, it will be called as L fabric. Surface lineations, which are restricted to the surface, just like slicken side. Slicken side are also one of the examples of these lineations. Okay, and non-physical geometric lineations such as fold axis and intersection lineation. So there is intersection between the two planes. Okay, there might be intersection of two planes, and it will give rise to the lineations or linear structures. Okay. These minerals and mineral aggregates. Okay, the minerals and mineral aggregates can form linear fabric by means of recrystallization, dissolution, precipitation, or rigid rotation. There can be any kind of process. Okay, there can be any kind of process. Um, there can be recrystallization, right? There can be recrystallization. There can be dissolution. There can be precipitation, or even the rigid rotation. So this may give rise to the formation of the linear fabric, right? There is something which is called as rodding. Okay, which is something which is called as rodding. Rodding means conversion of a mineral or elongation of a mineral as a rod. Okay, as a rod. Describe the elongated mineral aggregates that are easily distinguished from the rest of the rock. So from the rest of the rock, you will easily distinguish the minerals like this, which are in the form of a rod or the elongated nature. Okay, in the elongated nature. So this will be called as rods. Okay, so the quartz rods are common in mica schist and gneisses, where stripped quartz object. Okay, these are the stripped quartz object occurs as rods or cigars in the host rock. Okay, long appearances or longer the longer objects, the quartz material will be present. Okay, longer quartz material will be present in the rocks of these mica schist and gneisses. Okay, now budins. I've told you about the budins. Budins are the competent rock layers that have been stretched into segments. The lineation diagram which I have shown you just now. Okay, I've shown you just now, that is nothing but the budin. Okay, so these are the competent rock layers. Okay, these are the competent rock layers because they have left behind. Okay, they have left behind. Incompetent rock layers have been removed off. Okay, the incompetent rock layers have been removed off, and the competent rock layers which have been which is left behind took the shape of the budin. Okay, so individual budins are commonly much longer in one dimension. Okay, individual budins are commonly much longer in one dimension than the other two, and thus define a lineation. Right, you have seen. I'll show you once more. Okay, this is nothing but your budin structure. Okay, this is nothing but your budin structure. So individual budin. Okay, individual budin has, now you can see the contrast between the dimensions. Okay, you can see the contrast between the dimensions. One layer, okay, or one direction is large and very much elongated. Okay, but the other two dimensions, okay, other two dimensions, these two dimensions are compact. Okay, they are compact than this one. Okay, than this one. So this will be called, this will define the budding. Okay, this defines the budding. Right. Such linear buddings from where the x-axis of the strain ellipsoid is significantly larger than y. Okay, so x-axis of the strain ellipsoid is significantly larger than y. Right. So this is the condition. Okay, this is the condition of formation of the budding. The last structure for today, and that will be mullion. Okay, that will be mullion or mullion structure. Okay. Now, is the name that structural geologists use for linear deformation. Okay, here there is a linear deformation. This lineation is there. Okay, they are restricted to the interface between the competent and incompetent rock. This one. Okay, interface between the competent and the incompetent rock. These are the competent rocks. Okay, these are the competent rocks and these are the incompetent rocks which are getting eroded. Okay, these are getting eroded. But unlike the Boudin structure, okay, unlike the Boudin structure in which the Boudinage was present individually, okay, the Boudinage was present individually. Here in the Mullian structure, the incompetent rocks also are present, right? The incompetent rocks also are present, right? So competent and incompetent, both the rocks are present and both the rocks are seen, right? Both the rocks are present and both the rocks are seen here, right? And in the case of Boudinage, the incompetent rock has completely been removed. Okay, has completely been removed and it is not shown anymore, right? So this is all about lineation and foliation. Okay, this is all about the lineation and foliation structures. Okay, so this is it for today. We'll stop here.